I can't take attendance, so I'm just going to assume that everyone showed up to watch this uh, when I posted it on Blackboard. We did some things in the online lab that I want to talk about now in the lecture format, and some things I can do is I can use Blackboard, I can use slides, I can use all data, things I couldn't do out in the shop. So let me do what I usually do when I start these, is I go to Blackboard here and bring up the lecture. We'll go under lessons. So you should be able to see all this. And under there we have the week 8 slides. Click on that, let it open up. And let's go ahead and take a look at these slides. So what are we going to talk about? I don't know if week 8 is even accurate. I'd have to count. It would have been had things gone normal. But we're going to start talking. We spent most of the semester so far talking about inputs and processing inside the computer. So now it's time to move on to outputs. And so what do we have for outputs? We have solenoids. We have relays. Data streams, which, as you know, can be an input or an output. We have lamps and indicators. Things on your dash. Not just a check engine light, but all kinds of displays telling us things about the car, telling us about temperature or speed, digital dash, digital speedometers, all that kind of stuff. Even your XM radio, displays and things like that. We have DC motors. We saw some of those in our first lab. We have stepper motors, which it might take a little explaining. Ignition coils. Those are kind of unique as a computer output, but nowadays that's really what they are. They're no longer part of a separate ignition system. They're an output from the computer. So we talked about this in lab, the concept of direct versus indirect control. The idea that some outputs are controlled directly by the computer, some are controlled by a relay that's controlled by the computer. So a fuel injector is an example of direct control. The wires go from that injector straight back to the computer. Indirect control would be something like a fuel pump or a cooling fan or something that's a little heavier duty. And so the relay handles the current for that motor, and then the computer just handles the current for the relay coil, which is not very much. We also have two different ways of switching things. If the component is supplied power, and then the computer controls the ground, we call that ground side switching. If the component's always grounded and the computer sends power to it when it wants to turn it on, we call that power side switching. Still nowadays, most things are ground side switched. There are some, I think some GM fuel pump relays are power side switched, but almost everything is still ground side switching. So let's start with solenoids. Solenoids are actually the topic of the video that I'm getting ready to post right now. It probably is already up there by now, by the time you see this. But a solenoid is an electromagnet with a movable core. And it can be used to control liquid, vacuum or pressure, or mechanical movement. Important thing to realize is they can fail in two ways. You can have an electrical failure, so the coil, the windings can fail, or that might be perfectly fine. The electromagnet works fine, but the ports are plugged up, or it's full of rust, it's stuck. So you can do all the electrical measurements you want, but the solenoid doesn't actually do what it's designed to do. We see this kind of a lot with things like EVAP vent solenoids. You hear them click, but when you're smoking the car, they click. They're supposed to be sealed, and you still see smoke leaking out because they have a tendency. They're down under the car. Rust gets in there, corrosion. They won't seal up anymore, and the seat becomes, dirty, so it doesn't seat well. Solenoids can be normally open or normally closed. We talked about that in the online lab as well. So let me just look here. So this is a typical picture of a typical solenoid, and see if I can annotate here. So right here is the actual valve section of it, where this piece in the middle seals up against an opening. Clear that out. Here we have a spring, and the spring's job is to hold that closed. And then, of course, the vacuum source here. So when it's energized, essentially what's going to happen is vacuum is going to be able to flow from this port out that port. When it's de-energized, the spring is going to seal it up here, keep it closed. Notice the part inside the computer that's doing the switching is a transistor. We've seen these in class. And a transistor works a lot like a relay. You've got a very small, very, very small current here, controlling a bit larger current down this line here. So when this base current is turned on, it causes flow through the collector emitter circuit, and that completes the ground for this solenoid coil. I have a little video, so let me see if I can find that video. I have that on, let's see if we can make this stop. Go back to our Blackboard here. Same place you found those slides. I got a video on solenoids. So let's watch that. I may step away for a minute while that's going on, and then we'll talk some more about it.
This profile gauge can be used to measure the shape of irregular items to create an instant template for marking precise cuts, as it perfectly conforms to shape and holds its pattern. It is made in high quality, high strength, durable, and anti-rust plastic material, with its ease of use.
Hey there guys, Paul here from engineeringmindset.com. In this video, we're going to be looking more into solenoids and how they work. We're going to look at permanent magnets and how to see their magnetic field. We're going to create an electromagnet from a wire. We're going to be looking at some real-world solenoids, and we'll also cut one open using some power tools. And finally, we're going to learn how to build our own basic solenoid. If you are working with solenoid valves, you're going to want to download the Magnetic Tool app from Danfoss, who have kindly sponsored this video. The app makes it easy to test that your solenoid valve is working properly and works with both AC and DC versions. You can download it for free for Android and iPhone using the link in the video description below. So we'll start off by taking a look at a standard bar magnet. This is a permanent magnet. You've probably seen these type before. They have their ends marked. One end will be N for the North Pole, and the other end will be S for the South Pole. You can use its magnetic field to move other objects. If we imagine this iron nail as a piston in a valve, then we can see that the magnet can be used to move the piston. The problem with this type of magnet is that the magnetic field can't easily or practically be turned off. So in this case, the nail will stay attached to the magnet until we physically pull it off. If we place two of these magnets together, we will see that the likewise polar ends will repel each other, but the opposite polar ends will be attracted to each other. If I then place a compass near the magnet, we see that as I move the compass along the perimeter of the magnet, the compass is being affected by its magnetic field, and the compass face will rotate to align with the opposite polar end of the magnet. You see it also follows the magnetic field lines. Remember, opposites attract. We can see these magnetic lines if we place the bar magnet down on a sheet of white card, then we sprinkle some iron filings over the top. The iron filings are aligning with the magnetic field lines to create this pattern. These lines always form closed loops, and they run from the north to the south. As I mentioned, the problem with permanent magnets is that they are always on, and they can't easily or very practically be turned off or controlled. However, we can control an electromagnetic field, and we can generate that with some standard wire. Let's have a look. If we take this standard earthing wire and strip away the outer insulation, we find some copper wires inside. I'm just going to remove this with a sharp knife. Once it's removed, I'll just peel off one of the smaller wires inside. If I place a compass near the copper wire, we see that it has no effect on the compass. However, if I now connect a power source to each end of the wire, we see that as soon as I pass a current through the wire, current creates an electromagnetic field, and this will change the direction of the compass, just like we saw with the magnet. The electromagnetic field is operating in a circular pattern around the wire. If I place some compasses around the wire and pass a current through it, we see that they all point to form a circle. If I reverse the direction of the current, then the compasses will point in the opposite direction. If we now take the wire and wrap it into a coil, we can intensify the magnetic field. I'll just wrap this around a screwdriver and then compact it until it looks something like this. Now if I connect a power supply to the coil and pass a current through it, we see that the compass will be affected, and it now points at the end of the coil, just like it did with the permanent magnet. When I move the compass around the perimeter of the coil, the compass will rotate to align with the magnetic field lines. If I reverse the current, we see that the magnetic poles will also reverse. When current flows through a wire, it creates a circular magnetic field around the wire, as we saw a moment ago. But when we wrap the wire into a coil, each wire still produces a magnetic field, except the field lines will merge together and form a larger, stronger magnetic field. We can tell which end the north and south pole will be for a solenoid coil by using the right hand grip rule. This says that if we grip our hand into a fist around the solenoid and we point our thumb in the direction of conventional current flow, that's from positive to negative. It actually flows from negative to positive, but don't worry about that for now. But if we point our thumb in the direction of conventional current flow, then the thumb points to the north end, and the current will be flowing in the direction of your fingers. So if we have current flowing in this coil from positive to negative, so from left to right, then the current is flowing through the coil towards us, and the north pole will be on the rightmost end. We can check that because the compass will face the opposite direction. Remember, opposites attract. So one compass points north for the coil's south pole, and the other points south for the coil's north pole. If we then reverse the power supply, so the current is flowing conventionally from positive to negative, so from right to left, we simply flip our right hand over. The current is now flowing away from us in the coil, and our thumb points in the direction of north. Our compass points north to the coil's south pole, and the other points south to the coil's north pole. If we now look at this real-world solenoid valve, we see on the bottom there's a metal valve body, and on top is the solenoid within the blue box. So let's cut this one open and see what's inside the solenoid. I'll just place this one into the bench vise, and then I'll use the angle grinder to cut it open. I'll make one cut along the front side, and then I'll rotate it and cut down the other side. There's a few sparks coming out because we're cutting through metal on the inside. And there we go. This section has been cut out. If we look inside, we can see it's a pretty basic design with no moving parts. It looks like there's a solid copper ring inside, but that's just from the cutting blade. If we poke at the coil region, we will see it's actually a whole load of small copper wires all tightly packed together. With a little nudge, they will all fall out. Here's a much smaller real-world example without the protective casing. It's essentially the same, just a much smaller design and for a different application. If I connect this to a power supply, we can see that the piston can be pulled in by the electromagnetic field as soon as current starts to flow through the coil. If I cut the power, then the spring will force the piston back to its original position. I can remove the insulation tape to show that it's just the coil. If I then reassemble the solenoid and connect it to a power supply, we see that the piston is moved by the magnetic field and the spring. So now that we know how one works, let's make a very simple one ourselves. I'm just going to use this pen as the core body for the solenoid. I'll just cut this down so it's shorter in length. I'm going to use an angle grinder to cut this for no real reason other than I'm just being lazy and I like using power tools. Now I'm going to melt the ends slightly. I'm going to melt them with a lighter, and I thought I'd just show you this clip of a lighter from our new slow motion camera. This is filmed at 1000 frames per second, which is about 20 times slower. Pretty cool. So I'll just melt the ends with a naked flame, and then press the ends against a solid surface to spread them out. I'm I'm doing this because I want the ends to protrude slightly, which will make the coils easier to wrap. Now that I've melted and shaped the ends, I just need to drill through the excess in the center to allow the piston to oscillate. I'll also just file it down so it's nice and smooth and the piston doesn't catch on the edges. For the piston, I'm just going to use the iron nail. Now we need to wrap the coil. I'm going to use some 26 gauge or 0.4 millimeter enameled wire which I bought online. I'll leave some links down below for where to get that. So we simply want to wrap the copper wire as tight as possible from one end to the other. When we do that, we should end up with something like this. Then we need to wrap it a few more times in opposite directions to make it stronger. 3 or 4 wraps is probably fine. I didn't count the number of turns for this one as I'm just making a quick example for you. Once it's fully wrapped, we can just cut the wire and free it from the drum. And we want to just use some sandpaper to remove the enamel, which will give us a better electrical connection. So if I place my iron nail concentrically within the coil, but not fully within, you see that the nail piston is pulled inwards by the electromagnetic field as current passes through it. If we were to place a spring at the end, it would return to the original position. If we place the piston fully within the coil and then apply a current, the magnetic field will move the piston. And we could use this to provide a pushing force. Again, if there was a spring on the far end, then it could be returned to its original position. I just want to remind you to download the Magnetic Tool app from Danfoss for free using the link in the video description below. Okay, that's it for this video, but if you want to continue your learning, then check out one of the videos on screen now and I'll catch you there for the next lesson.
We're back. So that video was pretty good, I think. That guy, of course, every video I find seems to be that the person is speaking with some sort of an accent. I don't know what it is. So let's go back to the slides. Give me a minute. And they are here somewhere. Hopefully you're seeing this. I won't know until this video is all done and I look at it. So we talked in the lab, and I'll talk now about different ways that solenoids can be controlled. So what you're looking at here, we talked about ground side switching, power side switching. This is obviously ground side switching because we have 12 volts supplied all the time to it, and the computer is controlling the ground on it. So that's ground side switching. We move to the next slide here. We'll talk about ways that computers can control solenoids without actually just turning them on and leaving them on, turning them off and leaving them off. So one way is duty cycle. The output is pulsed on and off. So let's say that we had a solenoid that was capable of flowing 2 gallons per hour, but we only wanted 1 gallon per hour. We could just leave it on half the time. In other words, turn it on for a second, off for a second, on for a second. That would cut its flow in half. Think of it this way. If we had 1 gallon and we had a solenoid that flowed 1 gallon per hour, if we turn that solenoid on for 30 minutes and then off for 30 minutes, half of that gallon would flow through it. That would be a 50% duty cycle. Same thing could be accomplished by turning it on for 15 minutes, off for 15 minutes, on 15 minutes, off 15 minutes. In that hour, again, it would spend half of its time on and half of its time off. So if it flowed 1 gallon per hour, half a gallon would have flowed through it in that hour. If we only wanted a quarter of it, let's say 1 gallon per hour flow rate, but we only wanted to flow a quarter of a gallon, we only wanted to flow a quart, then we could turn it on for 15 minutes and then off for 45 minutes. That would be a 25% duty cycle. In other words, it spends 1/4 of the time on and 3/4 of the time off. So at the end of an hour, instead of a gallon, there would be just a quart flowing through it. Now we don't, duty cycles don't work in huge numbers like that. So, we're probably talking milliseconds. So in the lab, we did an example of an EGR vacuum regulator, and we were cycling it, on and off 10%, 20%, 30%. And, I'm sure each on-off cycle was only milliseconds long. Another way to regulate the flow through a solenoid is with pulse width modulation. The off time makes no difference whatsoever. Only the on time makes a difference. So instead of percent, when we're talking about pulse width, we're measuring in milliseconds generally. In the lab, I showed, I don't know whether you've seen it or not yet, I showed fuel injectors, and we were measuring the fuel injector pulse width. And pulse width is just a fancy term. Why they say width is, I guess, if you look at it on a scope or on a graph, the length of time it's on is a line, going across the screen like this. So how wide? What's the width of that line? On the oscilloscope, we saw that line lasted, a couple, 2-3 milliseconds. So the pulse width is 2 or 3 milliseconds on that injector. 6.5, according to this slide here, during acceleration, it could be 6.5. It could be 10. If you watch the video on the lab, you know it can get up higher than that too. So other things they use pulse width, I've seen like variable assist power steering. I've seen transmission electronic pressure control solenoids use pulse width. In fact, pulse width can be used to control current to things other than solenoids. For example, daytime running lights. I know some daytime running lights, in order to be, half brightness, the computer turns the power on and off to that light rapidly and can actually control the brightness of the light by controlling the length of the pulses that are sent to the light bulb. And that's not even a new technology. I think my son tried putting HIDs in an old Dodge Caliber, and because the daytime running lights use pulse width modulation, it could not fire those HID bulbs because it just wasn't a steady current to it. So again, duty cycle, we're talking a percentage. Pulse width, we're actually talking on time. How many milliseconds does something stay on? The off time makes no difference when we're talking about pulse width. So let's see. What is a solenoid? Think about that. If a solenoid comes out of the box blocking fluid and or vacuum flow, what type of solenoid is it? Is that normally open or is that normally closed? How can a solenoid fail? Hint, might find it on this slide. What does increased pulse width on a normally closed solenoid result in? Will we have more flow through it? Less flow through it? These are the questions inquiring minds want to know. And there's going to be a quiz, just for the record here. After this video here, this online lecture's been out a little while. Sometime this week, I'm going to put a quiz on Blackboard, and it's going to be due by Thursday at the latest, because then spring break happens, and we can't have anything due during spring break from the 10th to the 18th. Here's some other examples of solenoids. We got the fuel injector, which controls liquid. Variable assist power steering, that's liquid control. ABS, analog brake system. Typically, they use a combination of normally open and normally closed solenoids to control the brake fluid flowing to the brake. EGR vacuum regulator uses as a vacuum solenoid, obviously. Canister vent, another, it's basically air, vacuum, pressure. Trunk release is mechanical. Torque converter clutch, solenoid, control the fluid flow to the torque converter clutch. That can be pulse width modulated as well, or maybe even duty cycle on some older vehicles. So they're used all over the car. in all different systems. Let's take a look at ABS, for example. We'll go to this power that I like to use a lot. Give me a minute here. And let me find, I got all that up here somewhere. So we'll select that 2004 Chevy that we use a lot. I use that just because we have that vehicle out there. So if we look at electrical diagrams and interlock brakes, traction control, see what we can find here. A little difficult for me to see this from as far away as I am. Okay, so here, let me expand this. We have a series of inlet and outlet solenoid valves. And you know what they're the way they drew these, right? There's power supplied to them, all of these different solenoid valves, and then the computer's controlling the ground. This is the solenoid coil they're showing here. Let me just circle that here, right? So here's the power, switched power coming in. And then these are the actual solenoid coils, you know, and it shows the switching to ground. Of course, that's not a real switch. That's a transistor somewhere inside that module. So we have left front, left rear, inlet and outlet solenoid valves. The way this system works, the inlet valve is normally open, which means when it's not energized, fluid is allowed to go from the master cylinder directly through that solenoid valve out to the brake. If the wheel starts to lock up, that's when this valve is energized, blocks the flow of fluid to the brake, so no more pressure can hit the brake. It doesn't take any pressure away, it just gets rid of the pressure increase going to the brake. So no matter how hard you step on the pedal, no more brake fluid is going to go to the caliper. If the wheel is still locking up, so that's where the outlet solenoid valve comes in. So the outlet solenoid valve can actually release pressure from the caliper. So this is a normally closed solenoid valve. And when it's energized, it opens a passage, you know, out of that brake circuit to allow pressure to escape from that brake circuit. Let's see here. Sharing that a minute. So we can talk for a second. I think, you know, it would be better if we were face to face. You could ask questions and all that. And I don't really have the whiteboard available here, so maybe I'll have to set a whiteboard up behind me, because you know how much I like to draw, and you know how really I'm an aspiring artist instead of a teacher. But I think, you know, to kind of summarize, right? If we're talking about solenoids, you need to know that they can be normally open, normally closed. They can be just on or off. That does happen with some. Or a lot of times they're controlled by either duty cycle or pulse width modulation. Also, you know, when it comes time to checking them for their operation, the coil, a lot of times you can compare the resistance on the coil to make sure the wires inside aren't broken or sorted together, but that doesn't really tell you the solenoid's working. If you really want to know a solenoid's working, you kind of have to operate it. So if it's for example, the vacuum solenoid, like we did on the bench, we can apply vacuum to it and then energize it and see if it changes. You know, either releases it or begins to hold it when you energize it. Just doing an electrical test on it doesn't really tell you the whole story. Most solenoids are ground side switched, I'd say, in cars, you know. So they have power to them usually when the key's on and the computer controls the ground of it. Okay, what else? So we heard about duty cycle. We heard about pulse width modulation. Those are ways to control the amount of flow through the solenoid. Fuel injectors typically are pulse width modulated. A lot of other things are duty cycle. All right, let me bring those slides back up again. See if we can move along. Well, here's a typical fuel injector circuit. You know, it shows 14 volts. Of course, when the car is running, that's probably pretty accurate. Here would be the actual solenoid coil, and then the PCM is using a transistor to complete the circuit down to ground here. So, what type of solenoid is a trunk release solenoid? I don't know, maybe I'll have to ask that question on the quiz since you can't answer me right now. You can answer me on Blackboard. And secondly, a fuel injector is an example of what type of solenoid? Let's see, solenoid diagnosis. So knowing that there's two ways they can fail, you know, they can fail mechanically, but they can also fail, I mean, they can fail electrically, but they can also fail mechanically. So, you know, we can do a continuity or resistance check of the coil. A lot of times you're not going to find a spec. So, you know, if you suspected a fuel injector had an opener short in the solenoid windings, easiest thing to do would be to compare it to a fuel injector that's working. And the other thing, which is really not diagnosing the solenoid itself, but you're diagnosing the entire circuit, you can check to make sure that that solenoid's getting the power it's supposed to get, make sure it's getting the ground it's supposed to get. Most of them, you can remove it from the car, get yourself a 9-volt battery, and hook it to that solenoid, and it will operate. So if you're not sure if a solenoid's working or not, instead of really messing around with meters and measurements and all that, if you suspect the solenoid itself is the problem, grab a 9-volt battery, a couple jumper wires, hook it up. You can listen for it to click. If it's a vacuum solenoid, you can see if you can blow through it. See if energizing it opens and closes it. You try to blow smoke through it. There's all kinds of different ways. There's no one right answer for that. So that covers both the electrical and the mechanical operation of it. If you can bench test it like that, you can't always bench. It's kind of a pain to bench test a fuel injector. So, how could you test a fuel injector? Well, in fuel emissions, you probably did injector balance, where you pressurize the fuel rail, and then when you energize the injector, you see the pressure in the rail drops. You know that injector opened. If the pressure in the rail didn't drop, then you would know that that fuel injector did not open. So, like I said, there's more than one way to do these things. All right, let's go, before we talk about relays, I'm gonna just bring up, in the lab we use the example on solenoids. I had an old Crown Vic there. Let me take a look here. 1990 or 2001 Crown Vic, and for solenoid, the one I did, there's two I did. I did the EGR vacuum regulator solenoid, and I did a fuel injector. So I just want to look at the actual wiring diagrams for those so you can see. Here. Again, this is a little bit crazy that I'm pretty far away from this screen, so I'm having trouble seeing it. But here's, okay. Fuel injector 1, this is the one we tested in the lab. And what I told you was, there was a red wire, and that same red wire goes to all 8 injectors. And then the tan wire actually goes, here, let me actually goes to the PCM. So there's the powertrain control module. And, we have the tan wire going into pin 75 here. So in order to make this fuel injector operate, it's up to the electronics inside this PCM to create a ground on pin 75. When pin 75 is grounded, that fuel injector will turn on and fuel will spray into the intake manifold. The other one we looked at was the EGR vacuum regulator, so that might be a little bit more difficult for me to find this far away here. I'll get it eventually. Might have to slide my face right up close to you. Well, here's here's an example of a canister vent solenoid, which is same idea. We have power coming in on this red wire here. It says, right here, it says 12 volts, start or run. And down here, pin 67 of the PCM is where the ground is created. So if I were having a problem with this canister vent solenoid, of course, first thing I'd want to do is see, do I have my 12 volts here? If so, then am I getting a ground here at the other terminal to it? And I can operate that with a scan tool, force it to be a ground, and that way I can check to make sure that it's grounding. So I could replace this solenoid. Let me wipe this out here and do it again. I could replace this solenoid here with a Noid light, use the scan tool to turn on that circuit, and if the light lights, then I know that all of this wiring here is good. I know these connectors are fine, no problem with. And if the light doesn't light, then I got a problem with the circuit, and the problem is not the solenoid itself. Let's see if I can find that EGR vacuum regulator. Sorry, I got to stick my face right in here. It is a pretty small screen I'm dealing with. So oh, there it is. Okay. So this we did in the lab, the EGR vacuum regulator solenoid. So again, this is, you should be detecting a pattern here, right? So EGR vacuum regulator has 12 volts supplied to it from a splice somewhere. I'm going to assume that whenever the key's turned on, that you're going to have your 12 volts there. And the way that solenoid is energized is by the PCM grounding pin 47. This is an example of one of those things, though, that it doesn't just turn it on. This one uses the duty cycle. So depending on how much EGR flow we want, that's going to determine what percentage duty cycle. So this ground will be rapidly turning on and off. It's kind of difficult to measure something like that. But if you put a Noid light in place of this regulator, generally speaking, the higher the duty cycle you go, the brighter that Noid light's going to look. And when you get to 100% duty cycle, it should just be on solid bright. It's too fast of a cycle for you to really see it flashing. So, if you plug a Noid light in there, go to the scan tool and operate that EGR vacuum regulator like we did in the online lab, 10, 20, 30%, what you might see is a very dim light. And then as you crank it up closer to 100, the light's going to get brighter. That give you a pretty good idea that this circuitry is working, doing what it's supposed to do. Let me go back to our slides here. And we'll talk about relays some more. Now, relays, of course, in the first online lab, I did some demos of that. So none of this should be new to you. Just hoping to kind of embed it a little bit more in your consciousness here. So a relay is, used for indirect control of a device. So what does indirect control mean? Well, it means that the relay controls the device and the computer controls the relay. The idea behind this, is we want to use small current to control a large current. Probably the single biggest example is the starter relay, right? The starter, the current's huge, right? It's, 200, 300 amps. And you're controlling that years ago with a little ignition switch in the dash or in the steering column. And you know what the wires going down to a starter motor are? They're humongous. They're 0 gauge or 1 gauge. And so you can't imagine running those wires up to your ignition switch. It just wouldn't work. So for years and years, what the ignition switch actually did was just energize the relay coil, the starter relay. And when the starter relay contacts come together, that's what transfers the hundreds of amps to the starter motor. Now it's even different because on most cars, we're not even using the ignition switch to energize the starter relay. We're using a computer. You push a button, or you push the remote start on your key fob. You're just telling a computer, hey, please start the engine for me. And then the computer has to create the current flow through a relay coil that then allows that relay to close and send power to the starter motor. So it's kind of like a remote control switch. It's a switch that's operated by an electromagnet. So all we have to operate is the electromagnet, and then that switch will send the current where it needs to go. Typically, you're going to see a relay, any heavy duty load, anything heavy. What's heavy duty? Electric motors are always heavy duty. Bigger motors, power window motors, fuel pump motors. I can't even, not just motors, AC compressor clutch coil, high current load. A rear window defroster, that could be a very high current load. The blower motor on high speed for your climate control system. There's just example after example of things that are controlled by relays. So we'll bring up a wiring diagram again. We'll look. We did the Crown Vic cooling fan in the shop, and I know I brought the wiring diagram up on the screen for that, but it's not quite as clear there. We can do it much clearer here. So let's start with that. So back to electrical diagrams, and where are we? Heating and air conditioning, cooling system. Here we go. So here's the diagram for the cooling fan. All right. So one thing I didn't bother getting into in the shop demo was that this. Oh no. Wants to end the meeting on me because I'm the only one in it. The cooling fan is actually a 2-speed motor, so it has one ground, but it's got 2 different power feeds to it. So if power is sent to the motor on this pin here, this pin, it'll run at low speed, but if you power up this pin, the motor will run at high speed. So it's just the way the motor is wound. It goes through more coils through this terminal here than it does through this one. So I only showed you, a problem with the low speed relay, but they both work basically the same. So this is the right here. This is the circuit breaker. This is the actual current flow to the motor, this 30 amp circuit breaker. So any current flowing through that low-speed motor terminal, right, is flowing through this, dark blue wire here. So the key here to make this operate, we need to have this switch contact connect pin 30 to pin 87. So pin 30, I would say, is kind of the input, right? It's the 30 amp circuit breaker, so that can handle up to 30 amps. So it's going to be pretty heavy duty wire here, the dark blue wire and this yellow and black. So what's the computer's job here? So through this is another relay that provides power to a whole bunch of stuff when you turn the key on. So suffice it to say, that when the key's on, we need to see 12 volts here at pin 86. And then as long as pin 85 is grounded, that should energize the relay coil, and this is gonna cause that switch here to connect pins 30 and 87. Now, what causes this relay coil to get energized? Well, it has 12 volts to it. So the other thing we need is a ground, and so that ground is provided at pin 28 of the powertrain control module. So when the powertrain control module decides it is time to kick that fan on low, it's going to create a ground on pin 28. Here's a question for you. What's going to happen? How is it going to cause the cooling fan high relay to kick on? They're sharing the same power source here, both coils. Notice the high relay, that's got a 50 amp. Look at that, 50 amp. And this is this double squiggly line here. That's a maxi fuse. That's 50 amps possibly down this wire, orange and light blue, into the high terminal of the cooling fan motor. What's going to cause this high relay to kick on? So the PCM wants the low relay to kick on. It's going to ground pin 28. And then we're going to connect 30 to 87 here, send power down our dark blue wire to the cooling fan motor. What's going to cause that high one to kick on? So I just showed you 4-pin relay. I'm going to go back to that in a second. Two common types are 4 and 5-pin. So the 4-pin, just like we saw, it just turns something on and off. 5-pin, on the other hand, and those were 5-pin relays. They just weren't used that way. Let me bring it back up. So notice this relay has a pin right here, has a pin 87A also. And it's not connected to anything. But if that pin were connected to something, whatever was connected to pin 87A would be on right now. And when the relay was energized, what would happen is the switch contact would pull away from 87A and then, make the connection here. So causing whatever was hooked to 87A to turn off and whatever's hooked to 87 to turn on. So a 5-pin relay is kind of an either-or sort of device. A lot of times they stick 5-pin relays in, and they're only using 4 pins. So 87A, you look down in the socket, and there's nothing even in there. There's not a terminal in there. It's just blank. Not too uncommon. I could think something like this could be used for, low beams, high beams, right? So if the relay is de-energized, the power goes out 87A to the low beam headlights. When the relay kicks on, maybe it pulls it over, and now it's going to the high beams instead. Like solenoids, relays can fail 2 ways also. We had a Honda, the air conditioning wouldn't work, and I looked and the compressor was not kicking on, yet there was plenty of refrigerant in the system. There was really no reason why the compressor wouldn't kick on. And the funny thing is, you could hear the compressor relay, so the compressor clutch relay click, but the contacts inside the relay were so burned and corroded that even though they were touching each other, no current was flowing through them. So, here you have a relay, you're thinking, I hear it clicking, it's good. That's not necessarily the case. So just because a relay makes noise doesn't mean it has any current flowing through it. It was admittedly a strange one. You don't see that too often. But, just like a solenoid, it could fail electrically. So the relay coil has an open or a short. Or it could fail mechanically, so it gets stuck. I've heard of relays sticking on, and whatever is being controlled by it just won't shut off, even when you turn off the controls to it. So here's a picture of a typical relay. Let me see if I can, scribble on this a little bit. So we got a 12-volt source here, right? And that 12 volts is going to go through these contacts when they close, and then out to whatever it is we're driving, in this case, the fuel pump. This is the coil. So, this is what I would say is the control part of the relay, the low current part. Notice that low current circuit goes into the computer and through a transistor. Now, transistors typically don't handle a whole lot of current, so the coil it's got a fair amount of resistance. Not going to be much current flow on this circuit. On the other hand, these contacts, they're kind of heavy duty. They can handle a lot of current, and the fuel pump needs a lot of current. So when this transistor begins to conduct, in other words, when this little chip puts a little current on the base of that transistor, we're going to have flow through this transistor to ground. And so that means, our current's going to flow through that relay coil from this relay coil right to ground. And that's going to pull these contacts closed, and then current's going to flow through those relay contacts up to the fuel pump. So maybe some more questions I can throw out there on a little Blackboard quiz. Question 1 is name 2 common types of relay. I just talked about 2. The beauty of this is you can go back through these slides anytime you want. I'm running this right off Blackboard, so what I'm using here you can use. And if you remember, you have access now to all data, so if you want to look up these diagrams, you can look these diagrams up yourself. You can look through them. So to answer these questions should be no problem. 2 types of relay. And the second question, a relay uses a small current to control what? Here's some examples. Fuel pump relay, AC compressor clutch relay, engine cooling fan relay, battery saver relay or ASD relay, very common. Nowadays they provide power to most of the electrical system when the key's on, and then if you leave the vehicle for a while, they turn off so as not to kill the battery. To diagnose it, well, we did this in the online lab. We did a relay diagnosis. First thing we did was pull the relay out, and if you recall, we checked to make sure we had power and ground where we needed to have power and ground. Then we used some method to check the output. We bypassed it. So let's go back to all data and back to that cooling fan relay that we did in the lab. 2 places we checked to make sure we had power. We checked pin 30. Notice it says supposed to be 12 volts there. We checked pin 86. In that lab, I stuck a test light in both of those. So the relay's laying on the bench. I'm staring down into the open socket where the relay was. I stick my test light in, make sure the yellow and black wire is hot and the red wire is hot. That was good. Next thing I did, if you remember, I hooked my test light to battery positive. So now in order to light, it needs a ground. And I put my test light into this wire. Again, relay's on the bench, right? Relay's got nothing to do with this. Put the test light in there. I took the scan tool and I operated the circuit. So what effect did that have? Well, when I used the scan tool to operate the circuit, what I was really doing is asking the PCM to create a ground here. Once this wire was grounded, my test light lit. So I knew that this entire part of the circuit was good. I knew this part of the circuit was good, and I knew this part of the circuit was good. So my next question, what's the status of this part of the circuit here? The way I determined that, I just simply took a jumper wire and I made this connection with a piece of wire. And when I did that, what happened is the cooling fan motor kicked on. You can even hear it in the video, and I definitely heard it. So that told me that, that the motor's good. It told me this connection's good. It told me, this wire here is okay. It even tells me this ground is good. So it told me a lot of things in one quick little just jumping across these pins. So the question was a question for your report. Some of you did not write the conclusion down. Some of you did, but the question is, if I have power in these two places where I'm supposed to, and I get a ground here when I'm supposed to get a ground, and this circuit's good here, but my fan motor still won't run, what's the problem? There's really only one thing left, and it's process of elimination. We don't really have to test it. I can tell you that a lot of times vehicles use many relays that are the same part number. So one thing that's frequently an option is to swap relays. So I don't know if this high relay and this low relay are the exact same part number. They usually have numbers stamped on them. But if they were, just to verify, I would plug that high relay in place of the low, go to my scan tool, kick on my low fan control, and listen for the fan motor to run. So if it runs with the replaced relay, but not with the original relay, it kind of tells me what the problem is, doesn't it? You might even do that as a starting point before you check anything else. Again, there's not just one right way to do things. As long as you get to the problem without breaking anything, without doing any further damage, and you find the problem in a reasonable amount of time. You don't want to be wasting time taking steps that in no way could possibly lead to the problem. When it comes to relays, usually any circuit that has a relay, the place to do your diagnosis is right from the plug where that relay goes in. And the reason for that is the entire circuit comes together in this one spot right here. So you can test all four branches. You can test power here, you can test power here, you can test this, you can test the ground, you can do it all in one spot. You don't have to move your feet. Very convenient. So I do have one, I put it in red down here. You might hear an audible click when a relay is energized. It is not a reliable test. So going back to my example of that Honda AC clutch relay. It sounded like it worked, but no AC clutch until that relay was replaced. Okay, let me stop this a minute here. So to kind of summarize, because I'm not going to move any further today, that'll be the topic of our next online lecture. We'll talk about data streams. Today we talked about a couple of different kinds of outputs. We talked about solenoids and relays, and I tried to match it to the stuff that we did in the online labs a little bit. Here, hopefully you got a better look at the wiring diagrams than you could, I just had a camera pointing at the screen out in the shop when I was doing the labs. And, not as clear. Also, don't forget you do have access to all data yourself. So if you want to use that, that's fine. But I thought if I brought it up here, then you would be able to follow along a little bit better, and I was able to use the marker to kind of scribble things a little bit. So after you watch this, by the time you watch this, there should be, maybe a 10-question quiz that covers what we just talked about here. I'll put that up, and it should be pretty much right where you found this video, and do that quiz, and I'll just keep coming up with as much stuff as I can and posting it, and try to do as many quizzes as possible to make sure you're getting it. In the meantime, stay safe, stay healthy, and if I don't see you, have a great summer, and if you're graduating, best of luck to you.